Brought to my attention that there is a problem, which is the machine learning open house conflicts with the exam, which I hadn't realized. What is this thing? Why can't I get this to work? Hang on. So it turns out there actually is a conflict. So now I'm back to saying we should move the exam to after spring break. How is, well, yeah, I don't like it either, but I think it's not good to have it conflicting with the open house. So what do you think about Thursday, March 24th? Thursday, March 24th. When is the spring break? This would be after spring break. How much? I don't know. Does anybody know? I'm going to move this out of the way. Look at your schedules now and let me know if there's some problem. Any objections? Big conference that we don't know about, or Okay, look at your schedules and get back to me. Let me know if there's some problem with March 24th. If I don't hear back, I'm going to assume that's okay, and we will have to move it. So some of you are happy, some of you are upset. Can't please everybody. Also, one of the questions in the homework, I said to assume. You'll see there's a point when I said assume this is true. I realized you actually need to also put a log in there. Slightly stronger assumption. You can assume a little bit. That's a little bit stronger. Assume this holds. I forget which question it is, but you'll see that. It's a small point, but that's an H, yeah. In the very last question, I said prove something was consistent, and I didn't say, someone pointed out I wasn't clear about the consistency. Did I mean pointwise or L2? You can use either one. I think L2 will be easier, but whatever you want. That's in the very last question. All right, so we want to finish up the nonparametric classification. Any questions before I start? So we saw that any nonparametric regression estimator can be used as a plug-in estimator to turn it into a nonparametric estimator. And I think I mentioned briefly our classification trees are another nonparametric estimator. I just want to conclude with a few more. And in particular, I'll talk a little bit about bagging and random forests at the end. Let me just mention, though, that support vector machines, I divided it somewhat artificially, I think, into the linear and nonparametric version. The version I talked about earlier was to start off with a linear classifier of the form, sorry, this should be, yeah, that's good. This will be, and we're classifying with but the truth is, in practice, people usually use the nonparametric version. Which is simply to just, instead of restricting H to be linear, is we let it now be in a reproducing kernel Hilbert space. So this will be in some function space where we're restricting here. So this is going to so the nonparametric version just replaces the linear one with the reproducing kernel Hilbert space penalty. And in particular, I mentioned briefly in the other class that this numerically corresponds to simply replacing every instance in your algorithm where there's some sort of inner product just gets replaced by the kernel. So what is going on here is you're just minimizing the hinge loss subject to the condition that over all functions, but subject to the condition that the function is in a reproducing kernel Hilbert space. Another way to think about it is we're restricting over functions h whose reproducing kernel Hilbert space norm, let's say, is less than or equal to, some constant r. And so that's the nonparametric version of the support vector machine. And I wanted to just, it's not in the notes, but I just wanted to mention a typical kind of result that's available. There's many, many results, okay, about the performance of support vector machines. This is a particular one that looks a lot like the one I gave for, remember when I gave for the k nearest neighbors, I gave you two types of results, a kind of VC sort of looking result, and then a margin kind of a result. I forget which classifier I gave that for you, actually. Maybe it was the linear ones. So this is a particular result for support vector machines. This particular one is due to Blanchard, Bosquet, Massart. And it's actually, I'm not going to prove it, but it just uses Rademacher complexity arguments like we've used earlier in the class. Here's what the result says. For any h, for any h with this bound, some bound on its norm in a reproducing kernel Hilbert space, we have with probability at least 1 minus delta that the corresponding classifier, little h, will misclassify with probability less than or equal to, this is the empirical hinge error loss function, the training error, in other words, in terms of the hinge loss. This is what you're minimizing when you do a support vector machine, plus 2r over n times the sum of the kernel values plus this is a sort of concentration of measure type of term. It might seem a little bit weird. One of you asked about this the other day. What do you mean this holds for all h? Don't we want it to hold for the one that we're fitting from the function? But the point is it holds for every function in the class. Hence, it holds for the minimizer as well, which is the one that you're actually finding with the algorithm. So the minimizer, you're trying to make this training error small, trying to make this term small. But it holds for every function in the class. In particular, it holds for h hat. Small h is the sign of big H. It's the classifier you get from the function. Remember, you get big H and then look at its plus 1 or minus 1. Yeah, it corresponds in the geometric framework to allowing slack variables, to allowing things to cross the margin. It makes more sense in the nonparametric framework.
So just minimizing that loss function doesn't allow for...
It doesn't give you back the support vector machine, the general support vector machine. Okay, so this is nice because what this is saying is if there's, remember, you can think about this as how many things are close to the decision boundary in some sense, that margin. If this is small, this would make this right-hand side small. However, I think it's worth taking a closer look at this because there's a common feature to this bound that you see in a lot of kernelized results. So first of all, notice the regularization parameter shows up here. The bigger I let myself maximize over, this is going to get worse, but I could be getting a better fit, right? So there's a trade-off between, in some sense, just like in regression, like the sums of squares versus the complexity. So there's actually a trade-off there. This is only stated for a particular R. It hasn't accounted for the fact that we're probably going to optimize some sort of parameter. But also, what's often hidden in a lot of these kernel results is, what is this kernel? So let's take a typical kernel. The most commonly used kernel is the Gaussian kernel, but the Gaussian has another tuning parameter in it. And a lot of the literature doesn't talk about the fact that not only do you have to decide how much you're going to regularize, which means either how much you're going to restrict the norm, or if you write it in the variational form, how you're going to choose this lambda, but there's actually a choice of a parameter in the kernel. And people tend to not talk much about how to pick that. In fact, there's often just picked using certain heuristics. But it does affect this bound, because let's look at this. You know, when this is xi. So this part is 0. This is e to the minus 1 over sigma squared. Okay, so in this case, the probability is less than or equal to this term. Let's call this 1, so I don't have to rewrite 1, plus, and what does that become? This becomes e to the minus 1 over squared summed up n times, so it's 2r over root n e to the minus 1 over 2 sigma squared, plus the third term. The point is that in a lot of these generalization bounds for kernel methods, keep in mind that there's often another tuning parameter that's hidden in here. And again, there would be a trade-off, because you think, well, I can just make sigma small and make this, which would make this term small, but you might be increasing the training error when you do that. So I don't know much literature about the fact that when you do these RKHS things, that there's really another tuning parameter that you should, in principle, you should be optimizing over all the tuning parameters. But often people don't talk about this one very much. But anyway, that's an example of the kind of generalization bound that's available for doing support vector machines.
What is the exact meaning for any H here? It means that I can choose any kind of H as long as the normative H condition of this term.
For any H in the reproducing kernel Hilbert space ball, this inequality is true with probability at least 1 minus delta. Simultaneously over all H.
So it just means that the final error rate is closely related to the empirical error rate that you can get from H.
Well, plus terms involving the norm and things like that. Yeah. Okay.
I did want to show that the kernel SVM result is very close to the best result.
Yeah, so there's to show that this comes close to the Bayes error would take further assumptions. This is only giving you a bound. It's not saying that it's necessarily consistent or anything like that. In fact, I just gave you the simplest bound. In fact, you might want to look at this. If you're interested, you can look at this paper, and there's further bounds that make further conditions and then try to bound this right-hand side further.
Why is it 1 on the top of the exponential when you have the norm of x minus y for both xi?
Well, xi minus xi. Oh, it's. Oh, wait. You're right. That's a mistake. That's 0. That disappeared. However, so I lied to you. It doesn't show up there. But it does because yeah, that's a good question. So you're right. That disappears. But there's another sigma out front. yeah, actually, that's a good question, because what happens now, so you're right, that's e to the 0 is 1. I was thinking of the 1 over sigma to the front, out front, and if I do that, I get 1 over, what, root sigma? Sorry, that's 1 over, yeah, 1 over root sigma. But now I'm not so sure about that, because people often omit this when they're doing, you know, for kernel density estimation, we need this. For reproducing kernel Hilbert spaces, we don't need the normalizing constant out front. Yeah.
So, I mean, is that 1 over, I mean, so like when you're doing like Gaussian processes with the RDF kernel, right, you have two pre-parameters, right? You can choose the denominator in the exponential, but then you can also scale it, right, to increase the
Yeah.
magnitude of it. So those are two distinct parameters.
That's right.
So in this case, does that mean that it only depends on that scaling parameter?
Well, so it seems, but this is only an upper bound. So if I include the scaling parameter, it only depends on it through this, and but this is only an upper bound. This is so this is either way, whether I had the e there or this one. I'm not claiming this is sharp, and in fact, I don't think how the dependence on the other tuning parameter, as far as I know, is not clearly understood. There is a recent book, though, by Ingo Steinwart about support vector machines, where he has much more detailed bounds about support vector machines. So he might have bounds in there that explain more about the dependence on the other tuning parameters in the kernel. The other part that's missing in this, although it's pursued later in the paper, is, you know, these kernels, remember, are operators, and they have eigenvalues, and there's also an interaction between the spectrum, how fast the eigenvalues go down compared to the smoothness of the regression function and all that. So trying to further bound this into a tighter bound, you know, to say more about this right-hand side, you need to start introducing all kinds of information and assumptions about what the regression function looks like and so on. The bounds are much more complicated for this kind of stuff than for like kernel smoothing and so on. What's often hidden in all this, though, is, again, people just write in the kernel, but there's a lot of stuff going on in this kernel, such as other tuning parameters. Yeah, I don't know why I had the e to the minus, forget that term. All right, good. So making it from linear to nonparametric, though, was easy. That's the nice thing, right? Just replace the inner product with the kernel. If you want to get famous, though, I think if you write a paper explaining how the tuning parameters in the kernel affect things, I think that would be a very nice contribution, because I really don't think it's well understood. I want to mention two more methods. So boosting, what's going to happen for boosting is a very interesting thing. How many of you know what boosting is? It's interesting, right? Because the way these fads work is if I'd asked this question 4 years ago, everybody would have known what boosting was, because it was the hot thing. Now it seems to be less hot. Boosting is a very, very interesting thing. And what's going to happen is there'll be another guest lecture at the end of the month by my colleague, another young colleague. See, I get to force all my young colleagues to do this stuff. Sivaraman Balakrishnan, he's our new assistant professor in our department. He's going to give you a whole lecture on boosting at probably the last Thursday of the month. So I'm not going to mention too much about boosting now. Let me just say boosting is a very interesting method which combines classifiers. What you do is you take very, very simple, highly biased classifiers. So the typical example would be a tree, a classification tree, that's very, very, without maybe even just a single split. Like that would be a really bad classifier, right? Pick one variable and split on it. Or maybe just a few splits. A very, very simple tree. So a classifier like that is going to be highly biased. That's called a weak learner, because it's going to be pretty weak. And what boosting does is it does something like forward stepwise regression. It basically averages together a bunch of these weak learners, a bunch of these simple classifiers. And it effectively does something like forward stepwise regression, except classification. And instead of using 0-1 loss, it's using a loss like this, an exponential loss. So it's again using a surrogate loss. So think about trying to minimize this loss function, the expected value of this, over sums of simple things like small trees or something like that. And it's usually done in a forward, stepwise, greedy way. And what happened was Freund and Shapiro introduced this algorithm, and it was magic. It just seemed to work really well. And there was this question about why is it working so well? And it looked very arbitrary at first. And so what's going to happen is, to this day, it's very controversial. There's no agreement on why boosting seems to work so well. And what I have in the notes is what I would call the statistical explanation, which simply writes down what I just said. It's simply like a forward, stepwise fitting of a model of this form using this as a surrogate loss function. And you literally get back, when you cast it that way, you literally get back the AdaBoost algorithm, as it's called. But there are many people, including the inventors of boosting, who say that does not explain boosting. I mean, it might mathematically agree with boosting, but they say that doesn't explain why it's working well. And there's been other attempts to explain it. And so what Sivaraman's going to do when he comes is he's going to tell you the more, I would call them computational learning theory explanations of why boosting works. What is boosting and why does it work? So you'll get a whole lecture on that. And so I'm not going to go over it here. I'm going to leave that for him to cover. Yeah?
Are there domains in which boosting does robustly worse than alternatives?
Well, you know, for any classifier, of course, you can always find examples where it works great, and you can always find examples that break it. So that's always true. It seems to be remarkably robust. It seems to work well in a lot of situations. But yeah, you'll see articles where people, there was just an article a couple years ago saying, you know, all the explanations of boosting so far are wrong, and giving examples where it seems to work when it's not supposed to work, and so on. I think we're getting to the realm where now we're, you know, really high-dimensional, complicated problems. It's just hard to have general theory that gives a explanation for why something works. So it's pretty interesting. But he's going to cover, the stuff he's going to cover is sort of the latest stuff. There's actually a book, those guys just wrote a book maybe last year about boosting, very nice textbook. And he's going to cover some of the main theorems from that book that at least give you the creator's view of why they think boosting works. And what is boosting? For those of you who haven't seen it, don't worry, he's going to explain the algorithm. It's just an iterative algorithm. So I'm going to skip that, though, since he's going to do a whole lecture on that. I do want to mention a couple more, though. We already talked about cross-validation. So, you know, we talked about in regression, we talked about going from linear models to additive models. You know, so we did a transition from linear models. Then we talked about what we called additive models, which were sums of smooth functions. And then we talked about sparse additive models, where we fit models like this, but we force there to be some sparsity. You can use those for classification, too. There's no reason why you can't use a nonparametric regression function of this form. Even this, in fact, for a high-dimensional case, you're probably better off using the sparse version, using the sparse additive model. So you can just fit a model like this. And remember, we talked about the backfitting algorithm for fitting this and so on, even in the high-dimensional case. That's a perfectly valid way to do classification. You can also cast it, if you prefer, as a logistic regression. You know, for nonparametric regression, whether you use ordinary regression or logistic regression is not so critical, because in the linear case, the reason why we use logistic regression in the linear case is because when you look at a linear regression, that's not a good regression function, because we know the y in a linear regression is real valued, but we want usually to stay between 0 and 1, right, for classification. For nonparametric regression, that's less of a problem, because if I take a kernel smoother, let's suppose I have some data on the real line, but the data are all zeros and ones. So we're in a classification problem. So we have some zeros, some ones, some zeros, some ones. If I just do ordinary kernel smoothing, you're automatically going to get a smoother. You know, the kernel smoother is just a local average. It's going to stay between 0 and 1. You're not going to have the same problem you have with linear regression. So you can just use any nonparametric regression function, including an additive model, even though the data are 0, 1, and still get a classifier. Of course, you still need to turn it into a classifier according to whether the regression function is bigger than a half or less than a half. But if you want to, you can also, some people prefer to do this, to do an additive model, but to force it to take an additive form. So this is like a logistic regression model, but instead of linear, we're doing like an additive model. We're simply doing a sum of smooth functions. And what we do is we fit that using the log likelihood function for a logistic, plus typically in a high dimensional case, there'll be a penalty term for sparsity, just like we used before. I'm trying to see. It's going to be something like so if we fit a sparse logistic regression, but instead of having the betas, we allow there to be functions, but we have a penalty term like we did for additive models, you just get back, you're just going to get back a logistic fit, but many of these f hats are going to be 0. That's called sparse logistic additive regression. So actually, section 10, if you want the algorithm, I'm not focusing on algorithms, but the algorithm is actually written out for you. It turns out to be quite simple. But conceptually, it's exactly the same thing we did for regression. It's just that now the outcome is 0, 1. Probably for high dimensional classification, this is, again, probably a pretty good technique. My go-to techniques would be, I would try sparse logistic regression first, and then maybe sparse additive regression as my second thing, before trying any of these more complicated things. These are very simple, they're fast. They may work well, they may not work well, but you can try them very easily. So I'm not spending much time on these because I think they're just paralleling what we did in regression. It's very similar to what we did in regression, so I don't want it to be too repetitive.
Where do you get these f functions? Where are the space of the?
Well, it depends. So remember, let's go back to. There's different versions of it. So remember, when we go back to the additive model, you could minimize the sums of squares subject to each mj being in a reproducing kernel Hilbert space. That turns into a minimization problem. Alternatively, remember we did backfitting where you could just regress y on each mj minus all the other functions one at a time, the backfitting, and just use whatever smoother you like. The same is true here. You just do exactly the same thing. You fit the functions one at a time. There's many different ways to do it. There's many different possible implementations. But one way to think about it is, if you want to have a concrete version, is I'm going to minimize the Bernoulli log likelihood, where this is the probability of success, subject to some constraint on the FJs. A smoothness constraint, because it's nonparametric, and if you want, a sparsity constraint if you're in the high dimensional case. Okay, and you have many, many, many choices about how to do that. Any nonparametric way of doing that is fine. The particular one we put in, again, was just to do a one-dimensional smoothing method, iterate it, and then soft threshold it. That's the one that's in the notes. But it's just like what we did for regression, really. There's very little difference from what we did for the regression case. What I wanted to spend a little bit more time talking about was something that's quite different from what we did in regression, which is bagging and random forests. This is another example. I find this quite interesting because every year, if I talk about this, I look at the literature again to see if I can find good papers on this. And there's a real gap here between the theory and the applications. So for those of you who haven't seen it, let me explain what bagging and random forests are. And I'm going to try, I think I can give you a little bit of theoretical insight into why bagging helps. We're going to prove a little theorem that I think gives quite a bit of insight. But the full-fledged explanation of why random forests work is, in my opinion, still an unsolved problem. It's yet another example of where there's just this algorithm that just seems to work well in practice. And the problem with there's a lot of theory papers, and I don't mean to belittle them because this is a very difficult thing to study random forests. And the theory papers are all very good, but you'll see there's a huge gap between what they prove, which will be, let's just pretend we do a random forest using the following method. And it's usually not the same method we actually use in practice, because to analyze it, you have to simplify it. So there's this kind of gap. But let me back up and explain what's going on. What we're going to do, I started to mention this at the end of the last class. Let's start with bagging. Well, let's go back to trees, first of all. So we're going to start with a classifier. And let's say we've decided we're going to use classification trees. So remember, what does that mean? In 2 dimensions, it would mean I'm going to have some way of splitting. Ideally, it would just be, minimizing. This now becomes like an indicator function here and here. And if there's more ones here, we output 1 here. If there's more zeros here, we output a 0 here. So we get a well-defined classifier. It's a step function. We could minimize this cut over training error, but that's hard to do. Usually we use a smooth surrogate function. And we iterate. So now we might decide to split here and so on. So it's just like a regression tree, except we're classifying. Maybe we split an x1 here and x2 here. And we keep doing that. And at the end, there's going to be some sort of voting, which is really like a plug-in regression estimator. We're just checking whether the proportion of ones is bigger than a half or less than a half. And so, as usual, the tree is easy to use because a new patient comes in and you say, are their blood pressure bigger than this or less than this? And you follow them down the tree, and at the end you get a classification. And so trees are very simple, very easy to use, very easy to understand, and so on. But what people noticed about trees was they're kind of unstable. And that makes sense, right? Because you're making a definite cut somewhere. And if I'd moved this cut to the left or to the right, it could change the tree quite a bit. So the first improvement that came along, which is due to Leo Breiman, is bootstrap aggregation, or bagging. And it usually works like this. So I mentioned this briefly at the end of the last class. So we're going to take either a bootstrap sample. There's different versions of this. So I'll describe one version where we take a bootstrap sample, draw n times with replacement from the data. But we're not doing it for the reasons we bootstrapped in 705. We're not trying to get a confidence interval. We're trying to get a new classifier. So when we fit our tree, however we're fitting it, we're going to get, let's call it H1. Then we repeat. We draw another sample. Now, some people don't take a sample the same size as the original sample. Some people do. There's different versions of this. I'll just do the one where we take the same original sample size. We get a new classifier till we have m classifiers. And now we form an average. Let's call it h bar of x. We average those classifiers. Let's suppose there's b of them. Let's call that b, actually. And now we just let this vote. So again, the final classification, h hat, is 1 or 0 if h bar of x is bigger than a half, or, and less than a half. So at first, again, this was just an algorithm he put out there, and people started using it, and it was amazing. It just did much, much better than classification trees. So let me explain why I think this actually works. This explanation is drawn actually from a paper by Bin Yu and Peter Buellman. So I'll give you the reference if you're interested. Ben, Yu, and Buellman in 2002. And here's what we're going to do. What they do in this paper, which is very nice, is the beginning of the paper, they do a little trivial toy example where you can kind of reason through the theorem very, very heuristically and see what's going on. The rest of the paper is devoted to extending it to apply to more general situations. I'm just going to do the simple version of the theorem. What the theorem says is the following. The effect of bagging, of doing this bootstrap aggregation, is the following. It takes the original classifier, and you get a new classifier out which has approximately the same bias but reduced variance. So the effect of bagging is to reduce variance. That's the explanation they're giving for why bagging works. I think most people accept it. This is a pretty good explanation. You can think of it as almost like smoothing. We're starting with a very discrete object, and we're getting a tree out. And we're going to, by averaging trees, we get a kind of smoother object out, which has smaller variance. And we're going to prove this now explicitly. And we're going to do it in a toy example. It's not as complicated as a real classification tree. But I think it gives you the insight about what's going on. So let's consider a really simple case. We're going to look at the real line only. And we're going to consider, instead of considering decision trees and so on, we're just going to consider picking a splitting point here and taking a very simple function, which is a step function. So this is just like, when you do a tree, you're forming a piecewise constant thing. There's a lot of splitting going on. We're just simplifying all that and saying, let's just take the real line, pick one point, split on there, and form a 0-1 function. Okay? So this is a good way often to get a theoretical insight, is to consider a very simple function. And this is a function of x. Let's call this x. And we're going to define theta hat of x. The way we're going to split is based on the average. So we have y1 here to yn. And all I'm going to do is find y bar. And that's my split point. So whenever for any point x bigger than y bar, I'm calling this to be 1. Otherwise, it's 0. Right? So that's kind of the simplest version of doing something like a tree, where you're doing some sort of splitting. Everybody with me here? So we're just looking at a really, really simplified version. So what we're going to do is we get a random y bar, we form this function, and there you go. That's our split. It looks like this. Now, we can think about the mean and variance of what we're doing. So imagine I gave you a new data set. What would happen? Well, you'd get a different y bar. You'd get a slightly different function. So let's consider the randomness of this function at a particular value x. Now, it's pretty clear that if x, there's some true mean of y, and y bar is going to be, somewhere near mu, it's pretty clear that if you're at an x way out here, you're always going to get a 1. And if you're at an x way out here, you're always going to get a 0. So what's interesting is what's happening near mu. Okay, so what we're going to do is study x's that are close to mu. So to make that a little bit more precise, we're going to look at, let's say this is mu. We're going to look at a sequence of x's that get close to mu as n gets bigger, because that's going to reveal to us where all the variability is. There's no variability at the extremes. So I'm going to define xn to be, let's say, mu plus c sigma over root n. An xn very close to the mean. This is where this random function we're computing is going to be most variable. In fact, let's look at it. So if I look at y bar, theta hat at xn, what is that? By definition, that's the indicator function for y bar less than xn. Now I'm going to use the central limit theorem, which says that y bar is approximately normal with mean mu and variance sigma squared over n. Or in other words, y bar is approximately equal to mu plus sigma over root n times a standard normal z. So if I substitute that, this is mu plus z sigma over root n is less than, what was xn? It was mu plus c over root n. So that's just the indicator function for whether z is less than c. So at that point, this is a random variable. Right? If I imagine looking at that function up there, it's sometimes going to be 1 or 0. This is random. Okay? And we can compute the mean and variance of this thing. The mean of theta hat, well, that's just the probability that a standard normal is less than c. That's just the CDF. Okay? And the variance, well, this is like p. The variance is like p1 minus p. So this is so just to summarize, when we look at theta hat there, it's either 1 or 0. That's the only two choices. It's a Bernoulli. And it's going to be 1 with this probability. And there's a variance, 5c, 1 minus 5c. Okay. But now, let's look at the bagged version. So the bagging version, a typical bagging version, let's call it theta hat star of x, is going to be this is based on the bootstrap sample. What's the bootstrap sample? It's the average of these. But these guys, remember, are drawn from the empirical distribution function that puts mass 1 over n at each data point. So if I think conditionally on the original data, keep the original data fixed, the bootstrap sample is just an IID draw from some distribution, happens to be the empirical distribution. So conditional on the original data, we can still use the central limit theorem and say that y bar star is approximately normal. But what's the mean? It's the mean of this distribution, which is y bar. The variance is s squared over n. This was how we actually proved the bootstrap was valid in 705, was to apply the central limit theorem twice, to the original data and to the bootstrap sample. So I can write this as approximately equal to y bar plus, and we know that s squared converges in probability to sigma squared. So this is approximately this times, let's say, a normal again. Yeah, but it should be s, but s is converging in probability to sigma. So I'm using Slutsky's theorem. Yeah. So what? So this is the indicator function. Let's write it this way. I'm going to subtract y bar, multiply by root n, and divide by sigma. And so the expected value over the randomness of of the, let's call it E star. I mean, over the randomness of the bootstrap is the expected value of this thing. But let's now write what this is. This is basically Z. Sorry, this is, let's write it out, actually. This is, yeah. I'm taking the expected value of the only over the randomness of the bootstrap. This is the only random variable. So this is like a normal. So the expected value of this, again, this is like a standard normal from over there. So this is phi of C minus let's write out what this is. I'm trying to find a place on the board. How about right here? This is mu plus C sigma over n minus y bar over sigma. Oh, sorry. First of all, let me just finish this. I didn't finish this line. Right? This is just the randomness over the bootstrap. This is random. This is standard normal. So this is just phi of this. But now, this is a random variable still. This is phi evaluated at a random variable. What is y bar? Y bar is itself equal to mu plus sigma over root n times some random normal. So you can see the mu's cancel out, and all we're left with is phi of C minus Z. All right, I just took xn, where was xn defined? Minus this, mu bar. What's going on is, if you think about doing these bootstrap applications and averaging, you're just getting the expected value with respect to the bootstrap. So what you're getting is a random function. Imagine I draw this indicator function. I bootstrap, get another indicator function. I bootstrap, get another, and then I take the average. What does that average look like? It looks like a normal CDF. So what's going on? I'm running out of, okay, let's go over here. What's happening in a sense is that the original thing you're doing is very sharp. It jumps from 0 to 1. But when you do this many times and average it, you're just getting a kind of a smooth function. You're just smoothing this out. And now let's actually compute the mean of this over the randomness of the data, the original data. So I want to take the mean and the variance of this quantity. We already computed the mean and the variance of theta hat here. And now I want to compute the mean and variance of this thing. Let's in fact do the special case when we're right at the mean. So let's look at what happens when C is equal to 0. Then what's the expected value of this quantity? What's the expected value of phi of minus Z? So there's two levels of randomness, right? We're averaging over the bootstrap samples. That's the average we just computed. But there's the randomness due to the original data. That's what we're now computing. Minus Z has the same distribution as Z. What is the distribution of phi of Z? If I take a random normal and I evaluate this normal CDF at it, It's uniform 0, 1, right? That's anytime you take a random variable and then take the CDF of that random variable, evaluate it at the random variable, you always get a uniform 0, 1. Let's call it U. So the expected value of a uniform is a half. That actually agrees with this, right? When C is 0, this is a half. What is this when C is 0? It's a half times, I guess it's a quarter, right? What's the variance of the bagged thing? What's the variance of a uniform? It's a 12th, which is much less than a quarter. I hope that made sense. What's going on by bagging is you take that indicator function and you perturb it a bunch of times and average it, and effectively you're doing smoothing. You're taking something which was harsh and making it much smoother. The effect is the bias is not changed. In fact, at the mean it's not changed at all. In other places it is changed a little bit, but not much. But the variance is reduced substantially. And what the rest of their paper shows is that this is true more generally. Yeah?
So when we're averaging over a bunch of classifiers, each of the classifier has a tuning parameter, say, usually you choose that tuning parameter to do some sort of bias variance trade-off.
Not when you're doing these things. So we're not carefully training all of the classifiers when you do this. It would be, the hope is that that's taken care of by doing the bagging. And not, plus it would be very computationally expensive. The point here is that by, the point is that by using those many trees, they could all be pretty variable. And you're reducing that variable by doing the bagging step. Yeah.
Why is this only a constant factor on the variance?
Why is it only a constant factor?
What is it? I mean, it should be depending on some the number of bootstrap samples.
No, I'm explicitly assuming that the number of bootstrap samples is infinity, because I'm taking the expected value with respect to the bootstrap distribution. That's as if I took B to be infinity in the bootstrapping. So actually, in bagging, you take as many bootstrap samples as you can. And it's converging almost surely to its expected value, which is what this is.
So it's just a constant factor.
It's only a constant factor, right? But it is less. That seems to be the important thing. Right? That's right. So taking more bootstrap samples isn't helping because we're sort of doing it at B equals infinity anyway.
There's some kind of intuition to the shrinkage factor of
3, I don't know. I don't have any intuition why it's 3. And that's pretty particular to this example, actually. But I hope that the intuition, if there's any intuition, is simply that something smoother is going to be, when I wiggle this around, that's very unstable. And that's going to have a higher variance than something smooth.
What was the intuition of this xn? What was that?
Why did I choose that particular xn? Well, you could choose any xn, but you're going to see that there's very little change in the bias or the variance if xn is far from mu. Because when I draw these random functions, suppose I give you, data, you're going to get this. If I give you a second data set, it might look like this. And I give you a third data set, it's going to look like this. When you're far from mu, there's no variability anyway. So we're trying to look at the places where the variability matters the most, which is close to mu.
Why we should make a classification that y bar less than x?
No, I'm not saying you should use this as a classifier. I'm trying to create an example where we're getting a similar effect that you get with classification trees, which is making a cut somewhere. And it's just a simple case that we can study analytically. If you were doing one-dimensional classification, that is, though, what you would do, right? If you were using a classification tree, is you'd be first cutting somewhere, and then you'd be cutting somewhere else. It would be a little bit more complicated. You'd be making many cuts. You'd be counting how many zeros and ones there are there. This is meant to be just kind of a toy version of what's going on. And it's supposed to be showing you that when you make hard decision boundaries, there's extra variability that can be reduced by bagging. So it's just a toy example. As I say, the rest of the paper deals with the more realistic situations, but the intuition is still the same. Bagging is a smoothing operation. It reduces variance. Boosting, by the way, you can think of the opposite. Boosting starts with very small trees, which are biased. And by combining more and more trees, it's reducing the bias. So at a high level, boosting is a bias reduction technique, and bagging is a variance reduction technique. How are we doing on time? And you don't have to bag just trees, although that seems to be the most common use of it. You can bag other classifiers as well. There's quite a literature on bagging. But then the big breakthrough came when, so there was trees, then came bagging, which was like, wow, this works so much better than just trees. But by the way, though, you are losing something. The nice thing about a tree, as I've emphasized several times, is it's something simple. You can look at it. It's kind of interpretable. You're kind of giving up on that now when you're doing bagging. You know, if I'm averaging 1,000 trees, what is the thing I'm getting out at the end? It's kind of hard to interpret it. You're losing interpretability. On the other hand, if all you care about is high accuracy, then you don't care about that. So there is a trade-off here, though, between maybe getting better accuracy and versus getting something simple and interpretable. You are giving up on that. But then came another breakthrough, a famous paper, again by Leo Breiman, called Random Forests. And my sources tell me, who work at various industries, that they, in many companies, this is their classifier. This is the one that's one of the most commonly used general purpose classifiers. And it's hard to beat it. That's just hearsay, but that's what I'm told. And what's a random forest? It's exactly the same as bagging, except for one critical change. So remember, in bagging, we're going to take the data and build some sort of classification tree. Then we might take a bootstrap sample or a subsample, build some other tree, and so on. In random forests, the difference is just one major difference and one small difference. First of all, a minor difference is you grow big trees typically when you do random forests. You go all the way down until there's only 1 or 2 points in each leaf. So you grow as big a tree as possible. But there's one more randomization step. So we're already averaging a bunch of random trees. In random forests, when you go to make this split, remember there's some algorithm you have for making a split, right? You have some optimization you're doing. Which variable is best to split on and where is it best to split? You're minimizing some sort of loss function. When you do a random forest, instead of consider, every time you go to do a split, you don't consider, let's suppose you had d variables. You do not consider all d variables. You randomly select a subset of these features. Let's call it S, is some random subset of the features, and you only consider splitting on those, and you have to do this at every node. So when you go to do this decision about where to split, you first randomly select a subset of the features, and you only make your split decision on that random subset. Then when you go to make another one, you randomly select again. So there's an additional source of randomness. And there's no general agreement on how to pick this, although the default seems to be to take S to be about the square root of the number of features, but that's just a kind of rule of thumb. You don't have to do it that way. And that's the procedure. So we're going to bootstrap the data or subsample the data, grow new trees. At every node, though, we don't split on all the features. We split on a random subset of the features. And now you do the bagging thing.
So what's the intuition for why it is that you want to have those very complex trees for this?
Because it's hard to the idea is that if you take complex trees, you might be overfitting. But the combination of the bagging together with the taking random features seems to reduce the variability, so you don't need to worry about overfitting. And the purpose of selecting the random subset is in Breiman's original paper, he argues that the trees you get out at the end are less correlated. That kind of makes sense because you're not using always the same features every time to do the splitting. And in fact, he has a very crude bound, which I think I wrote somewhere, which is somewhat heuristic, which I've lost, but there's an upper bound on the generalization error, which involves something like something like something times rho, where rho is the average correlation between the trees. The average correlation between the predictions of the trees. And Bryman's argument, which is very heuristic in the paper, is that by splitting on random features, you create more decorrelated trees. The trees are less correlated, and so you get less correlation. Yes? So now there's this new thing in deep learning called dropout, and yes, it does sound a lot very similar to dropout, right? And so this is, in R, the package is called Random Forest that does this. I don't know what it's called in MATLAB. It must be similar to that. And you can set some of these parameters, and there's usually default settings. The big mystery is why this works. So like I say, I found lots of very, very interesting papers, and I don't want to belittle these papers because they are very interesting, studying the classification risk of random forests, but some of them say, under certain conditions, random forests are consistent. Well, consistency is, everything's consistent, right? I mean, every classifier, if you choose the parameters the right way, will be consistent. That's not very convincing. Some of them have rates of convergence and say under certain conditions you get good rates of convergence. Then you look at the paper and they say, but we're not going to use Bryman's real algorithm. We're going to assume that we never look at one of the papers, for example, says we're going to build the trees without ever looking at the data. I mean, nobody builds the tree that way, but it does make studying the theoretical properties much easier, right? So there's again, I'm not trying to belittle the papers. It's just because studying the theoretical properties of something like this is very complicated. So in my opinion, there's still a huge theoretical gap to explain. And the question isn't just to explain that they're consistent. It's why do they seem to beat other classifiers so often? Or rather, when do they beat them, I guess would be. What conditions are there that tell you that a random forest is going to beat a support vector machine or something like that? So to the best of my knowledge, there's still a big gap in the literature providing a convincing theoretical story for what it is that random forests are doing so well. Yeah, I kind of every year I look at the literature, see if there's anything new, and I actually went and talked to some of my colleagues, and no one seems to have a good answer. I do want to mention one paper that has a kind of a hint, in case you're interested in this. This paper, it's 10 years old now. It's by Lynn and John. It's called Random Forests and Adaptive Nearest Neighbors. It's still not a complete theory about what's going on, but there's a hint here of what might be happening. The paper's quite heuristic, but I don't mean that as a criticism again, because when you're studying complicated algorithms, sometimes it's very hard to make precise statements. But their argument is something like this. They try to make a heuristic argument that suppose you were doing k nearest neighbors. So the way we learned how to do k nearest neighbors is, you got some points. And if I want to classify here, I would just find the k closest points. And they try to argue that what's going on is that, when you're doing splitting, like in trees, you're actually considering neighborhoods of this form. After all, each tree is a partition of the space. And then when you start averaging trees, you're starting to combine partitions. So their argument is what these random forests are trying to do is find a kind of neighborhood with possibly a weird rectangular shape that might be more adaptive to the problem. In other words, instead of using a circular neighborhood, which is implicitly what you're using when you're doing k nearest neighbors, so by doing these splits, you're trying to find a kind of an adaptive shape to a neighborhood and do what they call adaptive k nearest neighbors. And they have some heuristics to suggest that's what's going on. It's not precise theory. But the argument here, which has not, to my knowledge, been fleshed out since then, is that random forests are doing some sort of adaptive k nearest neighbors where you're adapting the shape of the region over which you're doing k nearest neighbors. There was a question? Yeah.
Yeah, so it seems like you should be able to do this with k nearest neighbors in a much more straightforward way by transforming the distance metric between the points, right?
Right. You got to figure out how to do it precisely, and then you've got to show that it beats random forests. The ultimate test is, people are going to take data sets and try them out, and it either beats them or it doesn't. The nice thing about classification is you can check it. You either classify well or you don't. And of course, you will find data sets where you can build a classifier that'll beat random forest. That's not the question. The question is why, in general, and so often do they seem to work so well? So anyway, that's kind of a state-of-the-art method. And if one of you wants to get really famous, you could write a really good paper giving some sort of theoretical insight into random forest. That would be very useful. But there are theory papers out there, and if you're interested, you can certainly look at them. But you will find that there's kind of a gap between the true algorithm and usually what's used for proving things. You could do this for regression, too. I should have mentioned that as well. All right, so that's some nonparametric classifiers. I mean, I just wanted to mention a few because, again, it's in some sense, it's not that different from nonparametric regression.
How to do this for regression?
You just use y bar instead of counting how many zeros and ones are. You just take y bar. Whenever you do a tree, you take the y bar within each thing in each cell, and you get a piecewise constant regression function. And then you could average those. Some of the theory papers, in fact, are about the regression problem instead of the classification problem. All right, so we've had a taste now. Oh, yes, question.
So when you said that some of the theory papers assume that you don't look at the data when you figure random forest, does that mean like when you do the splits, you just do them at random?
Yeah.
Or something?
Right. You can see how that would simplify the theory quite a bit, yeah. All right, so just to review, we've talked about linear regression, high-dimensional linear regression. We talked about nonparametric regression, various techniques there. And then we talked about linear classification and very briefly about nonparametric classification. Is that about to start? Well, I guess we're not going to start.
Have your attention, please. Fire emergency has been reported in the building. Please leave the building.
We're not going to start minimax theory as I had planned.
Have your attention, please. A fire emergency has been reported.
But we will do minimax theory starting on Tuesday. So make sure you download those notes, and we'll go through them starting on Tuesday.